All right, we're open. Let's give a minute for everybody to get in, and then we'll start seeing our attendees come in. So everybody. All right, for everybody joining, we'll just take another minute or two for people to get settled, and then we'll start. Okay. All right, as we have attendees coming in, I'd like to just welcome everyone who's joining now to our continuing NHERI Lehigh seminar series, where we highlight people in academics and industry doing very important specialized work in the field of multi-hazard. So today's speaker will be introduced by Dr. Jim Rickles, the PI director of the NHERI Lehigh facility. So Jim, when you're ready, you can please introduce our speaker. And then right before that, I just want to make a note that we will hold all questions to the end of the presentation. You could use them in the chat and in the Q&A section, or raise your hand. All right, again, thank you, Jim. Go ahead.
Yeah, thank you, Tommy. Yeah, my name's James Rickles. As Tommy mentioned, he introduced me. I'm the director of the Lehigh NHERI facility. And part of our mission is to basically transfer technology and the latest research to the profession, including other researchers and basically the stakeholders. And so we have this series of seminars, of which one we have today, which is part of the Lehigh NHERI research seminars. So what we're going to do today is to have Professor Dimitrios Kalliontzis present his work, which I'll get to some of the details here about the seminar itself, but let me give you first some background about the presenter. Dimitrios is currently an assistant professor in the Civil and Environmental Engineering Department at the University of Houston. He has a research group that focuses on the behavior, modeling, and the design of reinforced concrete, as well as masonry structures. In addition to that, he's also working on developing a better understanding of the fluid structure interaction phenomena, particularly that which occurs during a coastal hurricane event, and that is in the coastal region. So something of very current high interest. Now, prior to joining the University of Houston, Dimitrios was a postdoctoral research in the Department of Structural Engineering at the University of California, San Diego. And there he is involved with looking at the seismic performance of pre-stressed foundation piles in one of the bridges in San Diego, which was the San Diego Coronado Bridge, looking to evaluate new design concepts for seismic resistant rocking bridge piers. Dimitrios, in terms of his academic background, received his PhD from the University of Minnesota, where he focused on self-centering precast concrete masonry wall systems. And prior to joining the University of Minnesota, he worked as a technical intern at SGH in New York and earned his Master of Science degree in Structural Engineering from Iowa State and received a Research Excellence Award for his work. Now, he's completed his degree, we call it a diploma, which is equivalent to, I guess, like a Bachelor of Science, but maybe a little bit beyond, but his diploma degree in Civil Engineering at Aristotle University in Greece, with a Master of Engineering in Hydraulic and Coastal Engineering. So with that introduction, I'd like to introduce the speaker, who will then present to you his entitled talk, Multi-Physics Simulations of Structural Responses to Fluid Flows Introduced by Coastal Hazards. So with that, I'll now give the podium to Dimitrios.
Hello, James. Thank you very much. And welcome everyone. So this is a work that we essentially started doing here at the University of Houston over the last few months. So it's very, very recent. and it has been mainly done by myself and one of my students, Vasilios Kotzamanis. So, the discussion is about fluid structure interaction. So, maybe I would like to give you a small background about what we mean by that. So, in a fluid structure, interaction domain, you have usually the fluid domain, which can be a force coming from wind, wave, or any other type of fluid. And then you have the interface, and then you have the structural domain. So usually how fluid structure interaction works is that the fluid domain will apply, generate some forces on the interface. Those forces will be transferred to the structure. Because of these forces, the structure will deform, and then these deformations will be affecting the interface, and then also the fluid domain. And we can approach this phenomenon in two ways. So first question we have to answer is, does the interaction really matter? In the sense that does what the structure is doing matter to the fluid? So then we have what has been mainly the case in how we estimate forces, even in current design procedure, is what we call a one-way fluid structure interaction. So you have the fluid forces developed to the interface and to the structure in one way, but then because the structure deformations are very small, you do not really need to transfer any information back to the fluid. And then you have the case where you have larger deformations. So then the interface is, you can say, like reasonably deformed, and therefore it does matter that you transfer the deformation information back to the fluid domain, and that is what we call a two-way interaction. And we can show that with a very simple example. That is a benchmark problem in the literature of what is called vortex-induced vibration. So you see here in this problem, you have a uniform inlet velocity from the left of the domain. And then in the first case, you have a very rigid structure, so the deformations are very small. Now in the case B, I call here, it's what they call like medium level structural deformation. So you still have some deformations, but are still not large enough. But even in this case, so you see on the right side, on the top graph, what we call the lift force. So the lift force is the vertical force generated on the structure by the fluid. So you see how the fluid force would essentially the fluid lift force would essentially vary as a function of just how the structure deforms. So one thing that is different is that the oscillation of the system changes, but also you have some variation in the magnitude as well. And then at the top, you see how the tip of this beam deflects in the two cases, where in one case it's pretty much almost zero deformations. In the other case, you still have some deformations, but they're not significant. And then you see another case where you have, again, the small, almost negligible deformations, and then you have large deformations. So again, you see how the lift force in the system that is shown at the top graph will vary, okay, as a function of the deformation. So depending on how much the structure deforms is it's an important component to making the decision either to go with one-way or two-way interaction. So in this presentation, I'm mainly going to focus on two-way type of interaction. So the question is that why do we care about all this in the structure or the civil engineering discipline? Is because we have a lot of phenomena produced in nature, such as hurricanes, tornadoes, tsunamis, that essentially produce some kind of fluid load. It can be wind, can be wave, and as our populations migrate towards the coast, more and more, then this phenomena is going to be more important for the civil infrastructure. So in the first,
Dimitrios, sorry,
yes.
Can I interrupt you a minute? Because we only see the first slide, your title slide. Are you still on that title slide, or?
Oh, really? No,
No.
I'm happy
I'm sorry to interrupt. So maybe if you go into presentation mode, that may that may work better there. Yeah, thank you. Sorry for interrupting.
Oh, okay.
I thought
Sorry
I'd give a
about
little bit
that.
of
Yeah, I
time just
didn't
to
know
make
that.
sure. Okay, thanks.
Yeah.
Thanks, Jim, I didn't pick up on that.
Yeah, I thought that the presentation was moving forward because to me it was, but how about now? Is it better?
Well, we see
You're
the
good now. You're good now.
background slide is now, and then.
Okay, okay, great. Okay, yeah, I was going through that. I thought that that was on. So yeah, basically, let me, if I go through a little bit back to my discussion so that everyone follows up what I'm talking about. So again, I try to go through a definition of fluid structure interaction. And then what I was mentioning is that in the fluid structure interaction, you have the fluid domain, and you have the interface between the structure and the fluid, and then you have the structural domain. So usually in the fluid structure interaction, you have the fluid forces transferred to the interface, and then to the from the interface back to the structure, and then you also have the structural deformations going back to the interface and then affecting the behavior of the fluid domain. So then what I talked about is so you can have two types of interactions. Either you have one-way interaction, and it's usually the case where we have very small structural deformations that may not be affecting the behavior of the fluid domain. And then you have another type of interactions, which is two-way, where you have large structural deformations where you do need to transfer the knowledge from generated from the structural behavior back to the fluid domain. So that kind of separates the two, one-way and two-way. And here I show one example of on trying to kind of address this question of why does the interaction really matters, and should we actually transfer the information back to the fluid? So in this case, what I'm showing is small level structural deformations at the top where the structure is barely moving, and at the bottom you see, let me try to go back and make sure that both videos play. So at the bottom you see what I call a medium level structural deformations, where you still have some deformations. They're not significant, but if you look on the right side, and what I have as the lift force, so the lift force is essentially what is causing the vortex-induced vibrations in this problem. It's the vertical force. So you do have a variation in the behavior. For example, you see that the frequencies of the oscillations vary. And also you do have some difference in the force that the structure is experiencing. Okay, and then I have another example where I compare this very small deformations case to where we have large level structural deformations, right? So in this case, again, you see that in the first case, where you have the small displacements, the frequencies of the oscillations are different. In the large displacement, the frequency of the oscillations is affected by this loop of information going from the fluid to the structure and back to the fluid. So there are many cases in nature that we may need to pay attention to this two-way type of FSI behavior. And then what I was saying is that why do we care about this in civil infrastructure is because we have many types of problems related to fluid loads applied to structures. That can be due to wind, that can be due to wave loading. And the first study that we tried to approach here at the University of Houston related to the elevated coastal housing. So why elevated is because in many cases when you have a coastal house near the shoreline, you do have waves, you do have surge, and by elevating the house, you do kind of reduce or even completely avoid the wave loading to the housing. However, there is a motivation still about looking into the wave loading affecting the houses, mainly because some of those houses were built with outdated guidelines related to the elevation, and also there is the the issue of the increasing hurricane intensity, that maybe in the future we will have to encounter larger waves. So in this type of problem, we try to kind of look into two sources of flexibility for the structural system. One relates to the effect of the timber-to-timber connection for light frame elevated coastal houses. And then we also looked at the SSI, or the effect of the foundation flexibility. So for this study, we tried to use an existing framework for simulation. So it's in Abacus. It's called a couple Eulerian Lagrange simulation. In fact, this is what is called an immersed boundary method that is being used in Abacus. Essentially, the nice about this method is that you build your Eulerian mesh and then you immerse the structure into this domain. It's also named in the literature as what is called interface capturing approach, where you only have to kind of use some kind of interpolation function to establish the interface between the structure and the fluid. So before we embarked on actually solving the problem that we're after, we tried to go and use some of the existing data to compare with what are the capabilities of this method in Abacus, and how well can it capture experimental data. So we looked at the problem that was solved. I think it was an experiment at Oregon State, where it was a wave maker that producing a solitary wave, and there was a relatively rigid specimen on the other end that was would experience the wave and measure the pressures on the specimen. So in the first comparison, we compared the wave profiles that was generated in Abacus and in the experimental setup. So in one case, overall, I think the wave profile was captured pretty well. There was only one case where we were not able to capture the wave. It was just before the crashing of the wave, and this could have been because of some nonlinearity at the discontinuity of the surface of the coast, and certainly this is an issue that we're still investigating. But there was also some numerical analysis before trying to capture this wave profile, right? The crashing, and was not able to. It was kind of they were having similar results to ours. So here is some comparison also on the pressure gauges that were on the specimen. So this is kind of more localized comparisons, and then some comparisons on the velocity meters that were also installed at different locations. So overall, I think the comparisons were pretty fair for our application. So we moved forward with modeling of a coastal house that was developed based on FEMA P499. It was some recommendations for the construction. So it was an elevated house, and it's light framed, and then it was also having some piles that were, I think, 10 times it was embedded into the soil, 10 times the diameter of the pile. This is some details of the finite element model. So it's based on shell elements for the front facade, and then that was also included the timber studs as stringers. That is an approach that is used currently in Abacus, and we also modeled the pile foundation with PY springs. So some of the parameters that we vary in our analysis, one was the effect of the connection flexibility. So one type of connection is a moment resisting connection, and then another connection that is kind of more typical for this type of houses. It's basically just providing a pin support. We also did analysis without considering the soil deformation. So basically the piles were constrained at the level of the soil, and then we also ran the analysis by considering the flexibility of the soil using PY springs in this case. So this is just a demonstration for three types of waves that we run with different height. So in one case, you see at the top case where it was a higher wave, it was causing a higher surge on the house. then a medium level surge, and then a smaller surge. So basically, in the third case, the wave was basically barely touching the house, but still was some surge and some force developed on the facade. Then based on that, we identified 3 types of phases in the interaction between the house and the wave. One was just when the house, just when the wave touches the house. The second is when the surge takes place and ends. So the velocity at the peak of the surge is 0, and then the splashing back starts as third phase. Then we compared the 3 cases of waves. So, I mean, this is very well expected that as you increase the height of the wave, then your forces on the facade are certainly going to be higher. One thing we also notice here in the case of the two worst wave scenarios is that you do have a peak happening, and then you have a drop, but then you have another increase in the force applied to the facade. And this is certainly because when you have the splashing back, then more the trailing edge of the wave comes in and then creates a second peak, which is not present in the case of the lowest wave. And of course, there is no quasi-static phase here, because after the wave crashes, then and the splashing back takes place, then you have all the water either withdrawing back or moving under the base of the structure. So one interesting result from this analysis was also that the flexibility of the structure does matter in the magnitude of the force that is being applied. So also I want to note that this is just a linear elastic analysis in terms of the material. So we certainly have to, as a next step, move forward with nonlinear material behavior for the house. But even without that, you see that as the flexibility of the house increases, then you do have a significant increase to the force. So here, what we compare as the green line is just the house as a rigid model. So there is no movement, and then you have the case of the moment resisting connections in the dashed blue line, and the red line is the case where you have the pin connections. So essentially going from the rigid to the more and more flexible structure, and you see how the forces increase. Now, why is that? The reason is because you have, as the facade deflects, then you allow more and more water to concentrate in front of the house. And as the trailing edge is approaching and more water is being concentrated, that is causing this increase in the force. And then you see here how that is demonstrated with the 2 types of connection on the moment resisting and the pin connection. So essentially, the front facade is acting as like as a bent, as a curved sea wall that retains increased wave volume, and that essentially was going to increase the force. And then we also compare that for the house behavior to the case of pile flexibility. So then we also took what we had and we added the foundation flexibility. So this is the dotted black line that you see here. In fact, this is also behaving similar to what we have before. So again, the foundation flexibility was causing a similar phenomenon where you allow more water to concentrate in front of the house, and as the stream of water is coming in, that is increasing the force. You also see that you have fluctuation in the force being applied on the facade, and this is basically what I would call as a semi-sloshing phenomenon, because you allow more water to come in, and then it recirculates locally in front of the facade that is causing this variation in the force. So as some conclusions to this first study was that when in the design of this type of houses and in many structures, maybe we need to reconsider the flexibility that comes either from the connections, from the soil, behavior, as it can certainly play a role in the interaction and of the waves to the coastal housing. Of course, like one case is that the coastal housing, in all three cases, regardless of if it was a small wave or larger wave, it may experience significant forces if the waves are allowed to surge on them. And this is certainly why FEMA suggests this elevation, but still, even with that, some of the existing houses are still going to experience some kind of wave loading because, again, their elevation was not calculated based on the most updated recommendations, and also there is a danger of increasing intensity, the hurricanes. So we may certainly consider new construction methods for this type of housing, or also try to think about non-conventional response mechanisms, as we can certainly have done for many years in seismic design. So in the second study, we also tried to kind of approach this behavior, this type of phenomenon of fluid structure interaction in a different way. That yes, 3D analysis, 3D elements such as what Abacus offers are great, but then in structural engineering, we are very well familiar and we really like using force-based elements. Right. So why is that? Is because we can certainly model, large structures with a lower computational cost and then still get very accurate results. Of course, force-based elements, they're well used in the Lehigh simulation facility, and they're very well known. They're also very well established in OpenSys and other type of softwares. So this is a classical force-based element that was developed in 1991 by Toscher, and then Spaccone was also kind of established that in a journal paper. And from then on, there have been also many improvements. There have been cases where plastic hinge integration was introduced, strain penetration effects. There are also another force-based element developed a little bit more recently at Lehigh to enable real-time hybrid simulations. There are also other methods that are being developed. From our side, I also did some work back when I was a postdoc at UCSD. We developed a force-based element to incorporate axial load, flexure, and shear interaction that doesn't currently exist in many of these elements. And again, the beauty of this is that you can model any type of structural members with just a single element. So you can think about that, how much important that is for the computational cost. So, but what is the concern of using force-based elements in FSI simulation? So first of all, they are one-dimensional elements. So essentially, they do not explicitly represent the physical structural geometry in the computational domain. So you have a tapered section, right? How are you going to capture this in a fluid structure interaction? And why is this important? Is because the shape of the structure does matter in the interaction. So this is like old knowledge for the CFD folks that have been studying this for a long time, even experimentally, both as well as in computational side or even analytical side, where we know that the shape of the structure does matter. So how are you going to capture this in a fluid structure interaction domain? So this is kind of what triggered me to kind of think a little bit differently and see how can we do that. So basically, based on that, I developed an in-house code for fluid structure interaction with the goal to incorporate force-based elements. So the idea is very similar to existing problems, and the loop that I described in the beginning of this presentation is still valid. So now the difference is that the fluid domain interacts with an interface that represents the physical geometry of the structure and essentially consists with a computational void. And the interface motion is essentially controlled by the force-based element, which is considered as a skeleton of this void that represents the structure. So you have the fluid forces transferred to the interface. then those fluid forces transfer into what they call what they call interface forces, and then the interface forces are transferred to the nodes inside the force-based element. So the force-based element through beam theory controls how the interface deforms, and then that those deformations are transferred back to the fluid. So this is how I try to kind of approach this problem and try to incorporate force-based elements in the FSI framework. So this is an in-house code that we developed. So it was based on what is called an ALE method, the arbitrary Lagrangian Eulerian formulation. So in this ALE method, basically what you're doing is that you are, instead of immersing the structure into the domain, instead the interface between the structure and the fluid is very well defined, and the motion is described by some kind of by the movement. It follows the movement of the structure. So some of the boundary conditions very similar. So it's non-slip condition at the interface. So essentially, what that means is that the fluid particles cannot slip on the structure on the FSI interface, and then you have force equilibrium on the interface. So just to demonstrate to you how this method works, instead of having a constant mesh, as in the immersed boundary method that we used in Abacus, so the mesh is moving by following the forces, by the movement of the structure. So you see this is happening, and what you see here, the structure, the interface is behaving as is following the motion that is dictated by the force-based element, and this is happening through this beam theory. So the governing equations for the force-based element. So in this cases, I just use a linear elastic element. So it's very the existing theory for that part. The force interpolation function is used in this element. I also use the consistent formulation for the mass matrix. So as you know, that force-based elements are based on the force interpolation function. So somehow you have to use a kind of method to come up with the displacement shape functions. And this is through a unit load method that I used. So now the big part of this formulation is the FSI interface. So what you see at the top is just a strong form of equilibrium at the interface. So what it tells you is that the stress is applied from the fluid are going to be equal to the stresses on the structure. So this is a strong form. However, if you try to apply that in a strong sense in a formulation like this, you may end up with significant instability. So what I did is that I applied that within a specified tolerance. So the stresses are essentially accounted as an unknown parameter, and then you solve for it. And then through some interpolation, you go from the interface that is shown here. So this is the FSI interface. Then the stresses are transferred to what I call element forces, but element forces again do not mean anything for the formulation. So you have to also transfer them into nodal loads. And this happens basically through equilibrium. And the compatibility in a similar sense, so again, the no-slip condition dictates that the velocity of the structure at the interface is equal to the fluid particle velocity at the interface. So again, this is based on beam theory. So, and it's approached in a weak sense, so that the fluid velocity is treated as an unknown parameter in order to avoid some instabilities, especially when you have added mass effects, which is a instability source for fluid FSI problems. This can be a significant issue. And then for small deformations, the mesh motion can be done with many different ways. There are many methods that you can do that. Now for small displacements, you can basically use a very simple Gaussian distribution. So in other words, the elements, the fluid elements that are very close to the structural interface move almost rigidly. And then as you move away from the interface, the motion of the fluid elements attenuates. And this is what is called arbitrary Lagrangian Eulerian formulation, because you can control the mass motion arbitrarily and does not affect the fluid motion. So then, because this is a new code, I had to go through some kind of validation. So I did do some model analysis of and compare it to to some results in Abacus. Then this is also some just to verify that the analysis works as intended. So here I had two cases where I applied an axial load, an oscillating axial load, and lateral load and the moment, and somewhere at the point between the two nodes. So then I kind of transfer that to the nodes, and then I compare these results to what to the Abacus analysis, just to verify that the way I applied it is correct. And then I also did some verification studies for the fluid domain itself. So there is no interaction here. So first I verified the structure part and the fluid part, and then as I will show you, the fluid structure interaction part. So in this case, I used the benchmark problem for the fluid that had three cases with different Reynolds numbers defining the problem. The first two are resulting in a steady flow, and then you have the third value of 200 that results in an unsteady flow. So for this case, I compared the forces, and then I did some mass convergence analysis to kind of see how well I can capture this. So in the two cases, you see that the force is just constant because it's a steady problem. And then in the third case, you see how the force varies since it's an unsteady problem. So then I moved into another benchmark problem. This is an FSI, fluid structure interaction. So this is for small displacements, so linear, geometrically near linear displacements. This is the comparison between the reference result and then the different analysis I run with different number of elements. So one thing I noticed is that basically the result for this type of problem is very, relatively insignificantly affected by the number of elements. So if you vary from 2 to 6 number of force-based elements, the result you get is pretty consistent with the reference, which is actually verifying something we know very well in structural engineering, that force-based elements are very powerful. And this is some comparison of this analysis, with a video that I have. In one case, I show the mesh. In the other case, the mesh is hidden. But again, the mesh motion here was very small, so it was not significantly affecting the results. It was mainly controlled by this Gaussian distribution, very simple case. And then I also tried to use a different type of analysis where I just have a vertical column. I did not have a benchmark problem to compare here, but I just tried to see how powerful is the code. So here you see an inlet velocity that is parabolic at the base. It has no slip, so kind of simulating a type of wind flow. One thing that was challenging in this analysis was the significant wake that was generated by the column. So you see those big vortex structures that are developed, and actually in order to, because, this is kind of always an issue in computational fluid dynamics, is that you have a significant wake, you have to make a long domain until the wake is numbed. But in this case, I tried to have a smaller domain and instead use what I call a backflow stabilization at the end. So essentially, when you have one important part here is the mass balance. So what gets into the domain also exits the domain. But if you have this big wakes, that creates a negative velocity, inlet velocity at the outlet that can lead to significant instability. So I use the backflow stabilization to enable this problem with a smaller domain as possible. And then more recent, I also used the co-rotational formulation for the force beam elements, for the force-based elements, and try to also compare to some experimental, to some reference results for benchmark problem. That is very similar problem to the one I showed before. Instead, the displacements, as you see, are much more significant. And also that showed a pretty good comparison. So just a summary for this study. Of course, we're not yet at the point to move towards studying effects such as waves or wind loads in a turbulent sense. But this is where we're heading with this code. But the first important step was to establish a code that can incorporate force-based elements and FSI calculations, have a correct representation of the geometry of the structure in the FSI domain, and then make sure that we verify with some benchmark problem to ensure that our code works as intended. And then the next step is to move towards material nonlinearities, two-phase flows, three-dimensional, and then eventually, hopefully, we can use that for hybrid simulations. Of course, there is a long ride until that can happen. And then this is some of the related publications. We're also presenting some of this work on TMI, and also publish some journal papers on that, but we're also still working on some of them. With that, I would like to thank you very much for your time, and I welcome any questions or suggestions.
All right, thank you, Dimitrios. I will open up the floor to anybody that wants to ask questions in the chat or the Q&A. Right now, I don't see anything, but we'll give it a few minutes. And then if anybody in the, any participants want to open up and talk, you can raise your hand as well, and we can open up the floor.
Also, I'm sorry for the beginning. I didn't notice that you were not able to see my slides moving forward.
No, not a problem.
I was able to.
Yeah, I just thought you were doing an intro still.
Okay.
No big deal. All right, so we have our first question. Joaquin Morris says, regarding the force and figure of slide 21 of 43, is this force, so if you want, you could pull that up, slide 21, is this force the load applied by the fluid, in parentheses, water pressure integrated in the facade surface, or the structural load perceived by the structure obtained from the structural model?
So let me see. So you're talking about slide 21. Okay, here. So the question is, let me see again. You're currently force slider. Is force is this for the load applied by the fluid or the structural load perceived by the structure obtained from the structural? Well, from equilibrium point of view, these two have to be the same. So the load that is, as I mentioned, this is equilibrium condition of the interface. So it's not only the pressure, it's the viscous effects that come in. It's not only the pressure that it's see, but the way we calculate it, if that is what is asked, is through the conduct force enabled in Abacus. But what the structural load perceived by the structure is equal to what the fluid forces are on the interface by equilibrium. I don't know. I hope that answers the question.
Well, if Joaquin wants to, if they want to respond, go ahead, please. Let me see. Another Q&A. Nothing yet.
Dimitrios, I had a question. I had my hand raised, so I can wait for Tommy to get to the others.
Oh, I do. I'm looking at the wrong one. So I'm going to lower your hand, but no, you can go ahead.
Oh, okay. Yeah, Dimitrios, very interesting, very, I think, important research. I had a couple just really for just further understanding, not to be critical by any means. And so those, the force-based elements satisfy local equilibrium. And so you have to incorporate that into the formulation. I guess you had that force interpolation function, little b of x. What I wanted to ask about is in the fluid loading, how were you representing that fluid loading on the element itself? I saw a point in the middle of an element but the fluid itself is distributed type loading. So was it represented as such? Because I think then the number of elements,
Yes.
if that's the case, is for force-based elements, as you show, you can get by with much fewer elements than if you use other formulations like displacement-based. So I think that point FSY is just an illustration, but it's continuous of what along the element you're integrating what over the length of the element, the pressure to get the essentially got to get the moments and the shears at the end of the element there, right?
Yes. Yes, that's a good question. So this is what it is called like a non-matching mesh approach. So you have approaches where you match the mesh. When you use even if you use displacement-based elements, it is very difficult to match the mesh in the fluid domain at the interface with that of the displacement-based element. It's still very difficult to do that, and I'm not sure how. So what you have to do, so these are meshed independently. Okay, so and this is also what this is attractive about this approach. So here, what I show you have the FSI interface. So the blue rectangles are essentially the fluid nodes on the interface. So on this interface, you discretize this interface with 1D elements for the 2D case. And then you estimate the forces produced at a single node. So these are essentially a horizontal and a vertical force. And then you have this lever arm that I call Y sub I. And that transfers that into loads on the interface, which is essentially axial, vertical, or shear, and moment. Okay, so the moment is basically produced by the lever arm. And then these element loads, you use equilibrium to just transfer them into nodal loads. So you have to go through this process, this transformation,
right,
to the element. So this is element loads, but again, we need nodal loads in the formulation. So then you use equilibrium to transfer them onto the nodes.
Yeah, so I guess the decision on how to space those fluid elements, because that seems to be one of the computational bottlenecks, in that the force-based element really is performing that BS transpose, KV times BS. The integral of that depends on the size of that matrix B, but you have to determine it, I think, based on the fluid loading. And so have you looked at, how we find, I guess it depends on the gradient, right, of the fluid force acting, but how we find is that mesh for the fluid loading have to be, because the finite element itself doesn't have to perfectly align. The force-based element doesn't have to perfectly align node by node. It could be longer as long as you integrate across the length, but depending on how complex that fluid loading is, that may take more effort. Generally, what's the relationship between the length of the element, say from node 1 to 2, and the corresponding fluid elements, which there may be several, right, between nodes 1 and 2 of the structural node?
I see. I think I see what you're saying. So in my formulation, I do not vary the force interpolation function. So based on how I model the fluid interface. So it can be, so usually the fluid interface has to be very refined in order to capture the forces. And this is the region where you try to refine that. Now the question is, does that affect the response of the structure? If you have, for example, higher modes, that could be the case. I mean, I'm not sure, but I see what you're saying. I think I know what you mean, that if you have the element loads, then the B function may not necessarily be the same, if that's what you're saying. But this is not something I do. So at the end of the day, the force-based element doesn't need to know how you discretize the fluid domain. You just transfer this element, this nodal force, this element forces into nodes. So the force-based element only get the nodal forces at the end of the day. So it does not really need to know how you discretize the fluid domain. I don't know if that answers the question, but
yeah, no, I understand. Yeah, but basically you have to integrate over the length. Any
Yes.
event, how long does it take to do some of the simulations? For instance, you showed us some very interesting simulations, and typically in the past, the computational aspect of the fluid and interacting with the structure. I think on the structural side, those calculations are usually pretty fast, but the fluid takes some time. How long does your simulations take to run? Let's say you had from real time to the time that it took to complete the simulation, the ratio.
So right now on my desktop, so for this problem I showed, so I will tell you something that may be very useful. So if I solve the CFD problem, so I ignore the structural deformations, and I only solve the CFD problem, I need 2 iterations. Okay, for per step. I use an implicit method. I use the generalized A method. I use 2 iterations. If I include the FSI interface, the FSI interaction, so I actually account for the structural deformations, then I would probably need 3 to 4 iterations per step. Now, if that's for small displacements. If I have large displacements, so then you get the geometric nonlinearity effect coming in, then I go up to maybe 6 iterations. So essentially, you triple the time from the CFD to the FSI, at least for the problems I approached. Now that can take probably like right now 5 hours, but still we have way to go in terms of the optimization of the code. We have done some vectorization in the element assembly and so on, but we're still working on that to further optimize it. Certainly, we're looking at different approaches because as you go towards hybrid simulation, this can be very critical. But this is not something that we have addressed. I just want to remind you that this work started about a year ago, and we still have way to go. We are at the phase that we're still developing the code capabilities.
Oh, no, it's very interesting. I didn't ask to be critical. I think you made a lot of good progress. It's an implicit formulation, I guess, the fluid. Have you looked at explicit or thought about explicit approaches where you don't have to iterate?
This is something we think about, yes.
Oh, okay.
Yes.
Anyway, so very, very, very interesting. I think this will really help to better define the fluid loadings and the interaction that occurs between them and the structure. So, we look forward to seeing some more progress on what you're doing there. Yeah, thank you.
Thank you for inviting me.
We have another question.
One question.
Yeah, if you want to read, you could read the question if you wanted to me verbally, if you want to read it out loud.
Yeah, I can read it. So it's what is the solid type that you use when you account for the flow? Okay, so this is something that we're also trying to look into different type of soils. So for this one, let me go, I think we use a saturated clay, but let me try to see if I can find that. Nope, we use saturated clay, I believe, for this one. But we are still looking at different types of soil. This is not the end of it. We're kind of trying to look into it. Yeah, we looked at the saturated clay. And then, did you rely on actual fluid data to estimate? Yes, I believe that the data that we got from this reference here are also based on experimental data that were used to derive the PY curves. Yes. Mm-hmm.
Okay. No other questions at this time. Jim, I'll leave it up to you if you have any final comments or conclusions to add to this, and then we could end the seminar.
Yeah, I first, Dimitrios, I wanted to, sorry, Tommy, I think you asked if I had any other comments or close the session.
No, that's it. If you had, yeah, you could close our seminar if you like.
Okay. Well, first, I wanted to thank you for your presentation. I think it's very informative. It's an involving topic, and I know a lot of people are interested in trying to use an approach like this. So I think your work would be very important, and I think the audience didn't have as many questions. I don't think they're overwhelmed. They're just probably fascinated by what you're doing there. I know it's not an easy thing to do when you're got a structural engineering background. This is kind of multidisciplinary. So with that, if someone wanted to get into this studying, I'm not saying this on my behalf, but just generally speaking, traditional structural engineers, what would they need to do? They probably need to do some studying, get some background in computational fluid dynamics, and then combine that with their knowledge of structural analysis to then be able to more competently, I guess, perform just analysis involving fluid structure interaction versus taking a structure and just putting predefined sinusoidal loads. I mean, is that what you would recommend if someone wanted to evolve into the field of fluid structure interaction?
Well, I'm not sure if I'm kind of entitled to answer this question, but I would do the same as I would do by having someone to study structure. I will start from structural mechanics. So then I won't go into the computational part, but mainly on the fluid mechanics. So the fluid mechanics started in a very similar manner as we started in structural mechanics, by analytical solutions. So if you go through them and you try to develop an understanding of how, what is the Reynolds number, what is the Fruits number in terms of when it comes to torsion wave and so on, try to understand this, what is the importance of its aspect in the analysis. Then after that you can go to the computation side. But this is how I would start. It's certainly not an easy issue in terms of it's an interdisciplinary, it's another discipline, but still it's mechanics. So I would start in a simple way, and also there are many a lot of information nowadays on fluid structure interaction on the web. So there are many classes offered. So I think you start simple, and then you based on that develop, go deeper and deeper as you move forward.
Okay, yeah, thank you very much, sir. So I don't know if the audience has any other questions, Tommy. I didn't see.
No, that's it. We could we'll close up.
And we lost a few participants, and so I should thank you then, Dimitrios, and your presentation will be archived, and I think there's contact information in case anyone in the audience or anyone that views the your presentation in the future, they'll contact you there. So we look forward to you preparing and submitting a research proposal and seeing some good things come out of this. And so with that, I'd like to thank you and the audience also for attending. And if you have any questions from the audience that come up in your mind, you can either send them to us, we could forward it to Dimitrios, or Dimitrios, you can receive those directly. I don't know, Tommy, if we archive the QA part.
No. All of this whole thing gets archived as a video. We put on the Design Safe website eventually.
Okay, so sorry, Dimitrios, we have a few logistical questions here. Anyways, thank you very much, Dimitrios. And so we should let you go and we'll move on, and look forward to seeing you soon. And I should tell the audience, Dimitrios, you came to one of our researcher workshops where I think you had some ideas that we hopefully generated. So I wanted to encourage the audience, and you should pass the word to come to the research workshops. We have 2 every year. Most sites have 2, and you'll gain a lot of knowledge and some ideas how to use things that perhaps you didn't even realize existed to further your research. So we're looking to support Dimitrios in that regards. Okay, thank you, Dimitrios. So I guess, Tommy, with that, we could probably close up.
We will close the session at this point. We appreciate everybody's time and time coming to listen to this seminar. All right, thank you.
Thank you very much.